In this particular section, we're going to discuss testing a hypothesis. And many of you may be familiar with the term hypothesis from your science classes and use of the scientific method. In statistics, hypothesis is a claim or statement about a property of a population. In the first couple of sections, what we're going to do is we're going to be testing an hypothesis for the population mean. And the way that we're going to do that is by taking a random sample and determining the sample mean and making an inference about the population mean from our sample. So in statistics, hypothesis is a claim or a statement about a property or a population. And that's very important, particularly researchers in such fields such as medicine, psychology, and business, which need to test hypotheses in order to make decisions. Here's an example of a hypothesis. The average delivery time for Domino's is 30 minutes. This used to be their brand many years ago. In fact, their commercials would indicate that they would deliver the pizza within 30 minutes or the next pizza was free. And the company had to discontinue that as their brand because a number of their drivers were involved in serious accidents, and it resulted in a class action lawsuit against Domino's. So they no longer use that as their brand. So we want to talk about the various parts of an hypothesis that we want to identify. The null hypothesis, denoted H sub O, and this is red, null hypothesis, always states that the population parameter is what we believe it to be. The important thing to note about the null hypothesis is that the null hypothesis always contains a condition of equality. So you will see or identify the null hypothesis by less than or equal to, greater than or equal to, or equal to. But nonetheless, it will always contain a condition of equality. Now, if the null hypothesis is not true, then the alternate hypothesis must be true. The alternate hypothesis, denoted H sub 1, and its red alternate hypothesis, always contains a statement of inequality. So it's going to contain less than, greater than, or not equal to. So again, the null hypothesis, denoted H sub O, always contains a condition of equality, whereas the alternate hypothesis always contains an inequality, less than, greater than, or not equal to. Now, what we will be testing in the next couple of sections is a hypothesis test. We're going to be conducting a hypothesis test for a population mean. So we're going to gather information from a sample, and we're going to compute the sample mean, and based upon our sample mean, we're going to make some inferences about the population mean. So from the previous statement, which was Domino's will deliver the pizza in 30 minutes, what we want to do is to identify our null hypothesis and our alternate hypothesis. Now, the easiest way to do this is to first of all identify the claim. And once you identify the claim, then it's easy to determine whether that claim is the null hypothesis or alternate hypothesis. So in the previous statement or hypothesis, we had the average delivery time for Domino's was 30 minutes. So that means the average delivery time for Domino's is equal to 30 minutes. Now, remember that the null hypothesis has to contain an equality. So here our null hypothesis is that the average, and this is a hypothesis test for a mean, so we're stating here that the average delivery time for Domino's Pizza is 30 minutes. So we have an equality. So this is our claim, and it's also our null hypothesis. Now let me caution you here that the claim can be either the null hypothesis or the alternate hypothesis. It's not always, the claim is not always the null hypothesis. However, the null hypothesis always has to contain an equal to. Now, once you identify the claim and you decide whether that's the alternate or null hypothesis, the other one is easy to write, because once we identify the claim here, and the claim here happens to be the null hypothesis, but that will not always be the case, again, to write the other one, we just take the complement of the claim. The complement of mu is equal to 30 minutes would be mu is not equal to 30 minutes. And again, remember that the alternate hypothesis always has to contain inequality, a condition of inequality, where the null hypothesis always must contain a condition of equality. So let's look at these again. And let me back up for just a minute. Please do not write this. Do not write this because it makes no sense. Do not write h sub o is equal to 30. That makes no sense at all. The null h sub o refers to the null hypothesis. What we're trying to test is, this is a hypothesis test for population mean. So we need mu in there. So do not write h sub o is equal to something, or h sub 1 is not equal to something. This is a hypothesis test for the population mean. So do not write the null hypothesis is equal to 30. That makes no sense. Null hypothesis is a statement. What's equal to 30 is the population mean, or that's what we want to test. So again, what we're trying to do is simply, in this particular section, is identify the null and alternate hypothesis. And again, what I would do is, first of all, I would read the particular hypothesis here, or the particular statement, and first of all, identify the claim. Identify the claim. Now, the claim can be either the null or alternate hypothesis. So here is our statement. A chemist claims, so we know that something very important is going to follow this word. A chemist claims an additive increases the life of an automobile battery. If the mean life of the automobile battery is 36 months, then what are the hypotheses? Again, this is an hypothesis test for a population mean. Now remember that the alternate hypothesis always contains a condition of equality, whereas the alternate hypothesis is going to contain a condition of inequality, either less than, greater than, or equal to. So we have a chemist here, and he claims that if we use his particular chemical in this automobile battery, then it increases the life of that battery. So that means that the claim here is that the mean life of this automobile battery is going to be greater than 36, because it's going to increase it beyond 36. So our claim here is that the mean life, which is mu, is going to be greater than 36. Now, again, it's easy, or if you would try to identify the claim first. Now, remember, the claim can be the alternate or the null hypothesis. So in this particular case, the claim is actually our alternate hypothesis. The claim is actually the alternate hypothesis. Chemist claims that if you use his ingredient here, formula that he's developed, then it will increase the mean life of the auto battery. So that means that the mean life is going to be greater than 36. Now, again, the alternate hypothesis always contains inequality. It's either going to be greater than, less than, or not equal to. Once you identify the claim and identify it as either the null or alternate hypothesis, the other one is easy to write. Here the claim is mu is greater than 36. Now, if a number is greater than 36, the complement of that would be a number is less than or equal to 36. The complement of mu is greater than 36 would be mu is less than or equal to 36. Now, remember, the null hypothesis always has to contain a condition of equality. So again, what I would encourage you to do is, first of all, identify the claim. Once you identify the claim, decide whether that is the null or alternate hypothesis. Remember, the claim can be either one. What determines whether the claim is the null or alternate hypothesis is whether or not it contains a condition of equality. And here, if we're going to increase the life, then that means that we're going to make the mean life of this automobile battery greater than 36 by adding this chemical. So the claim is that the mean life of the battery is going to be greater than 36. So identify the claim. Once you identify the claim, determine whether it's the alternate or the null hypothesis. So here it would be the alternate hypothesis because it's strictly greater than. And then once you do that, what you do is find the complement of the claim. And if a number is greater than 36, then its complement would be some other number is going to be less than or equal to 36. And this is called a right tail test, since and the interest is increasing the battery life. So this is what we call a right tail test. And that's going to be very important later on when we actually start testing hypotheses. We're not actually testing hypotheses here. The only thing that we're doing is identifying the null and alternate hypothesis, which is a very important part of that procedure. But this is a right tail test because it reads something is greater than some number. A contractor wishes to lower heating bills by using a special type of installation. If the average monthly heating bill is $200, then what are the hypotheses here? Again, what we've got to do is read in between the lines, and the first thing that you need to do is identify the claim. So this contractor has this special type of installation, and if he claims that if you use his installation, then you can lower your monthly heating bill below the population mean. So here, again, we need to identify the claim. The claim is, and this is a hypothesis test for a population mean again, so that's why I have mu here. The claim is that if I use this special type of insulation the contractor is providing, then my average monthly heating bill will be lower. Well, lower means less than. So the claim here is that if I use this insulation, then my mean heating bill will be less than the average of 200. So this is my claim. And since it involves a statement of inequality, my claim is the alternate hypothesis. Remember, the alternate hypothesis always contains a condition of inequality, whereas the null hypothesis always has to have an equal to in there somewhere. Less than or equal to, greater than or equal to, or equal to. So once we identify the claim, we simply take the complement of the claim to obtain the other hypothesis. So if mu is not less than 200, then it must be greater than or equal to 200. So here are your hypotheses. And again, I should have pointed this out. The alternate hypothesis determines what type test you have. It determines the type test that you have. The alternate hypothesis, not the claim, but the alternate hypothesis. Now here the alternate hypothesis happens to be the claim, but in general here the alternate hypothesis, H sub 1, determines what type tail test you have. And this is a left tail test, which is going to be very important later on when we start actually testing hypotheses. This is a left tail test since we are interested in lowering heating costs. If it reads mu as less than in the alternate hypothesis, then it's going to be a left tail test. If it reads mu is greater than in the alternate hypothesis, it's going to be a right tail test. But again, the easiest way to decipher and determine what the null and alternate hypotheses are is to identify your claim first. Once you identify your claim based upon how it reads, then you're going to decide whether that claim is the alternate or the null hypothesis. And then to obtain the other, you simply take the complement of it. Again, a claim can be the null or alternate hypothesis. It does not necessarily, it's not always one or the other. So a claim can either be the null or alternate hypothesis. But the statistical evidence can only support the claim if the claim is the alternate hypothesis. If the claim is the null hypothesis, that means it contains an equal to somewhere, then the statistical evidence can be used to reject the claim or fail to reject the claim. No matter which hypothesis represents your claim, you always begin a hypothesis test by assuming the null hypothesis is true. So when you perform a hypothesis test, you make one of two decisions. You either reject the null hypothesis or you fail to reject the null hypothesis. However, I must caution you here. The only way that you can be absolutely sure whether the null hypothesis is true or false is to test the entire population. And in most cases, that's not practical because it would not be cost effective, or it would just simply be too cumbersome to do that. So what you're going to do is you're going to make your decision to reject or fail to reject the null hypothesis based on your sample. So you must accept the fact that sometimes your decision is going to be incorrect. Again, the only way that you can be absolutely certain that the null hypothesis is true or false is to test the entire population. And that more or less defeats the purpose of taking a random sample. Again, we're going to base our decision to reject or fail to reject the null hypothesis based on that particular sample, because it, again, may not be practical to test the entire population. It might be too cumbersome. The population may be too large. It might be too expensive. So again, we're going to base our decision to reject or fail to reject the null hypothesis based on our sample. And there is a possibility that we could make the wrong decision. So there are two types of errors that we're going to discuss. And the type 1 error occurs if the null hypothesis is rejected when it's true. So here are our two conditions. We're either going to reject or fail to reject the null hypothesis. If we reject the null hypothesis when it's actually true, then we have committed a type 1 error. That is, we're rejecting the null hypothesis when it is true. If we reject the null hypothesis and the null hypothesis is false, then we've made the correct decision. If the null hypothesis is false and we reject it, then we have made the right decision. A type 2 error occurs when the null hypothesis is not rejected when it is false. So here we go. If we fail to reject the null hypothesis and the null hypothesis is true, then we've made the correct decision. We don't reject it because it's true. However, if we fail to reject the null hypothesis and it's actually false, then we've made the wrong decision. We have what we call a type 2 error. So type 1 error occurs again if the null hypothesis is rejected and it's actually true. So if we reject the null hypothesis and it's actually true, then we've made the wrong decision. That's a type 1 error. If we fail to reject the null hypothesis and it's actually false, then we've made a type 2 error. So let's look at another example. Here, the USDA limit for salmonella for chicken is 20%. Meat inspector reports that the company exceeds the USDA limit. You can perform a hypothesis test. So we want to perform a hypothesis test. So the first thing we have to do is identify our claim. And this is not actually a claim for a population mean. This is actually a claim for a proportion. A proportion is a ratio. It is a percent, etc. So here we have a percent. So this is not actually a mean. It's actually a proportion. So I'm going to use P instead of mu. Now the claim is that the salmonella exceeds, which means that it is greater than 20%. So that means that the proportion of salmonella is greater than 20%. That's my claim. So since that's my claim and it contains a condition of inequality, my claim is actually my alternate hypothesis. So P is greater than 20%, written as a decimal, that would be 0.20. So again, what you need to do is identify the claim first, and then decide whether the claim is the alternate or the null hypothesis based on whether it's strictly an inequality or whether it contains a condition of equality. So once we identify the claim, and it happens to be here the alternate hypothesis. Now remember, again, the claim could be either the null or alternate hypothesis, depending on whether it contains a condition of inequality, that's alternate, or equality, which is null. Now once you identify the claim, then to write the other hypothesis, you simply take the complement of that. So if P is greater than 0.20, the complement of that would be P is less than or equal to 0.20. And remember that the null hypothesis always has to contain a condition of equality. So let's see if we can identify the type errors here based on these particular statements. What error will occur if the contamination is less than or equal to 0.2 and you decide to reject the null hypothesis when it's actually true? So here we're saying, okay, we're saying in the first statement here that the null hypothesis is actually true, and you reject it. In other words, you say, oh, I don't believe that the null hypothesis is true. I'm going to reject it. So what happens here is that you're rejecting a true null hypothesis. So you're rejecting the null hypothesis when it's actually true. So when you reject the null hypothesis and it's actually true, that is a type 1 error. So this is type 1. Now, why is this even important? Well, if the USDA inspector rejects the null hypothesis when it's actually true, in other words, the percentage of salmonella is less than 0.20, then that's going to cost the company money and create an unnecessary health scare, because they're going to have to recall the product. And they're going to recall the product, and it's going to create lost revenue. It's going to create bad or ill will among the consumers, when actually the inspector was wrong. He rejected the null hypothesis when it was actually true. Now, type 2, we're not much better here in reference to our error and the problems that it will cause. Now, when the contamination is greater than 0.2 and you fail to reject the null hypothesis. So let's go back to our different type of errors here. So here the contamination was greater than 0.2 and we failed to reject the null hypothesis. Well, that is a type 2 error. We should have rejected the null hypothesis because the null hypothesis was false. The null hypothesis stated that the contamination was less than 0.2. So we failed to reject a null hypothesis when it is actually false. So we failed to reject the null hypothesis, and what would happen is that if this null hypothesis is false, which means that the contamination is greater than 0.2, then the contaminated product goes out to market, and that could result in that contaminated product being sold, which would put the consumers at a health risk. So those are the two different types of errors that we make in hypothesis testing. Now, we're only going to be examining type 1 errors. And the type 1 errors are called alpha errors. And that's where we run the possibility of rejecting a true null hypothesis. So alpha here is the level of significance, which is the maximum probability that you're going to assume in making a type 1 error. The most significant levels are alpha equal to 0.1, alpha equal to 0.05, and alpha equal to 0.01. For example, if you use the significant level of alpha equal to 0.10, then that means that there's a 10% chance of rejecting a true null hypothesis. Simply multiply by 100 here is what you're doing. So if you choose alpha to equal to 0.01, then that means that there's only a 1% chance of rejecting a true null hypothesis. The probability of making a type 2 error is denoted by beta, and in most cases that cannot be determined easily, so that type of error, as far as computing that, is beyond the scope of this particular statistics class. So what we're going to focus on here is the maximal probability of making a type 1 error, which is going to be denoted by alpha. So in this particular section, again, really what I want you to gain from this is being able to break down a statement and determine what is the null and alternate hypothesis. And again, the null hypothesis, denoted H sub O, always contains a condition of equality. It's going to have a less than or equal to, greater than or equal to, or equal to in it. In other words, there will be an equal to somewhere. Whereas the null hypothesis, denoted H sub 1, always contains a condition of inequality, less than, greater than, or not equal to. And when you break these down, always start by identifying the claim first, and depending upon whether that claim has an equality in it or whether it's strictly an inequality, determines whether the claim is the alternate or null hypothesis. Now keep in mind that the claim can be either one, but once you identify the claim as either being one or the other, then it's easy to write the remaining hypothesis by simply taking the complement of the claim.